The next ones we're going to look at then are geometric series. Now the series again are just the terms of a sequence being added together. And so if we have a geometric series, that's going to be based then on a geometric sequence. Add the terms together in a geometric sequence, you'll have your geometric series. Because it's geometric, there'll be a common ratio between each of the successive terms in the series. So for the geometric sequence 2, 4, 8, 16, 32, common ratio of 2, we'd write that as 2 plus 4 plus 8 plus 16 plus 32, which would give us then a sum of 62. So very similar to the arithmetic series, but just now dealing with geometric patterns. If they're a shorter series, then again, just going through and adding the terms up together is often the quickest way to go, and you can often do that in your head. But as they get longer, it's going to be more convenient to use then these general terms. So these are on your formula sheet, of course. We are looking at the geometric sequences in series, and so the second one here and the third one here, those two are going to be the ones for our series. Now do note for both of those r cannot equal 1, and that just is because the denominator for both of those would go to 0 if we sub in r equals 1. But for any other r value, these ones are going to work, and then those will give you then the value of each of those series. Don't forget as well that the general term for a geometric sequence is also going to be valid when looking at series, and that can often be helpful for finding the number of terms or say the last term. Now the second equation is really just the first equation, just with that general term put in for there. So if we look at the derivation of that, I have r times t to the n, and then minus t to the 1, and then all over top of r minus 1. So what I'm going to do is I'm going to put in this t1 r to the n minus 1 in for my tn term here. So it'll give me Sn r, and now my tn will be written as t1, and then r to the n minus 1, all subtracting t1, and then r minus 1. So if I look at my numerator here, what I'm going to do is I'm going to factor out that t1, because both of my terms in the numerator have a t1 term. And so it'll give me then t1, and then in brackets, I'll have this r times r to the n minus 1 in the bracket, and then minus 1. And I have a full bracket around there, just because I factored the t1 out of both of those terms. And then all still over r minus 1. So then if I simplify this just a little bit, so I have t1 here. Now this is r to the 1, and so r to the 1 and r to the n minus 1, when I multiply those together, because they have the common base, I can just add their exponents. And so I get 1 plus n minus 1, and so that just gives me actually n as my exponent. So I get r to the n minus 1, and then all over top of r minus 1, which we can see is the same as that second equation that we had there. So they are still the same equation, just written in terms of different variables. So looking at a couple of examples, we want to start by coming up with a common ratio. So if I go 16 divided by 2, I get 8. 128 divided by 16, I get 8. And 1024 divided by 128, I get 8. So I have a common ratio here of 8. My number of terms, of course, is just going to be 6. And so then my t1 is 2. And so I can then very easily find then S6, which is the sum of those first 6 terms. So I'm going to use the equation t1 r to the n minus 1 over r minus 1. And I'm using that equation because I don't know what the last term is. Now I could certainly find that using the general term and use the other equation. But here using this equation, I can just fire values that I already have in. And so it'll be my quickest solution then in this case. So my t1 is 2. My r value is 8 to the power of 6 minus 1. And then all over top of 8 minus 1. And if you put your values in for that, I will get 74,898. For this next one, we're going to do the same thing. We'll find our common ratio. So 1 divided by 0.5 is 2. 2 divided by 1 is 2. So I can see that my common ratio is going to be equal to 2 in this case. Now I don't know the number of terms in this series, but I know that t1 is equal to 0.5. And I know that the last term, which will be tn, is equal to 256. So it turns out for this one, I don't actually need to know, if I use that second equation, what then the actual number of terms is. So I can take r times tn minus t1 all over top of r minus 1. And so my r value is going to be equal to 2. Tn, which is my last term, is 256. I can subtract then that 0.5, and then divide all of that by that r value of 2 minus 1, and that'll give me a value of 511.5. Now you could certainly use the general term to find the number of terms, and then use this equation to solve for that. But because we have this equation here in terms of tn, I can actually solve these without ever knowing what that number of terms is. For the last one, we're looking for the number of terms in this particular series, and we're told that the sum is equal to 16,400. So for here we can see 15 over 5 is 3, 45 over 15 is 3. So I can see then that my R value is going to be equal to 3. My T1 then is going to be equal to 5. I'm looking then for my number of terms. My Sn, for however many terms I have, that'll be that 16,400. So I can set up my equation here as my Sn equal to T1, and then I have R to the n minus 1 over top of R minus 1. Now I need to use this equation because this is the one that has n in. The other form of that sum equation has a Tn, but I don't know the last term. It doesn't have then that n in this equation. So I can put my values in for this. I'll get 16,400, and that'll be equal then to 5, and then I'll have 3 to the n minus 1 all over top of 3 minus 1. So here I can multiply that 2 times that 16,400. It'll end up then with 32,800, and that's going to be equal then to 5, and then 3n minus 1. I can move that 5 over, so dividing by 5, I'll get 6560 equals 3n minus 1. If I add the 1 to both sides, I'll get 6561 equals 3 to the n. Now certainly for these ones here, you could just trial and error those. So try different values for n until, so 3 raised to the power of that until you get 6561. Or as before, we could also use our graphing calculator. So what I've done for this one here, in y1, I put that 6561 and then 3 to the x in y2. I'll graph this one out. Now keep in mind, I do need this y value, or my y-axis has to include this. So I just set my y-axis equal to 7,000, so just a little bit higher than that constant term. And so then we can go second trace, and then go to that intersect value. And so enter, enter, and enter. And then we get x equals 8. And so that tells us then that I have n, or 8 terms in this particular equation. Again, you could trial and error these as well. We'll keep those n values relatively low. But to solve for those n values, we won't until Math 30 have an algebraic way of solving for those. So just use your calculator and you can come up with those relatively easily. Now an extra set that we have with the geometric ones is infinite geometric series. And so we could have an infinite series that actually has a definite sum. This never works with arithmetic ones. Some infinite geometric series actually do have a sum. Now if the geometric series has a sum, what we say is that it's a converging series. If it doesn't have a sum, we say it's a diverging series. And for the diverging series, there is no sum to there. We just say it's undefined. But if you add it up, it would say go to infinity. The difference here is going to be your common ratio. So if you have a converging series, that's where that common ratio R is somewhere between -1 and +1. The series will be diverging if that common ratio is either greater than 1 or less than 1. So basically outside of the range for the converging series. Again, it can't be 1 because then we're going to get 0 in the denominator. So we have this fourth equation under the geometric sequences and series, or on your formula sheet. That's this equation down here. Now this only applies to infinite series, so please don't try to apply this then to finite series. And then you see this range here as well. So R must be greater than -1 or less than 1. So this is giving you the range for which this applies. If your R value is outside this range, again, it's just a diverging series, and so you don't have to calculate anything. You can just say that your series is, or that the sum is undefined. So the terms here, Sn is just the sum, T1 is the first term, and then R, of course, is the common ratio. So when you're doing these, first decide whether your R value fits inside the defined range. If it does, then you can sub it in. If not, then just say undefined. So for the first one, we have 0.5 divided by 2, 1.125 divided by 0.5. If you check either of those, you'll get R equals 1/4. T1, of course, is 2. And so then I do have a sum for this one here, and I'll have 2 over top of 1 minus 1/4. And so that will give me then a sum of 8/3 for that first set. For the second one, 25 over 625, 1 over 25. That gives me an R value then of 1 over 25. Again, that's between plus and minus 1 there. And so this one will also be converging. So I get T1 equals 625, and I can put all my values in. So my sum here, 625, and then all over top of 1 minus 1 over 25. And my sum then, in this case, and I'll leave it as a fraction, 15,625, and then all divided by 24. Now in this one here, to find my common ratio, I'll go 21 over 6 divided by 3, or 49 over 12 divided by 21 over 6. And what we'll see in each case is I get r equals 7/6. Now 7/6 is greater than 1, and so it's outside of my domain, and so this then is going to be undefined.